Hi, this lesson is on Thermochem Chapter 16, and it is a Gen Chem 2 lesson. This is going to go over the highlights of Chapter 16, and it is also touches a little bit on what we did in Chapter 5 in Gen Chem 1. So we are going to talk about spontaneity and entropy. Some of these words may sound familiar to you. We're going to talk about the laws of thermodynamics, some of which we've already done in Chapter 5. We're going to talk about free energy, calculating thermodynamic quantities, and then we're also going to look at free energy with the equilibrium constant. So let's start by talking about spontaneity and energy. Or actually, let's start by talking about thermodynamics. What is thermodynamics? Well, thermo, you know, has to do with heat, and dynamics has to do with movement. So basically what we're going to focus on in this energy, in this unit, is the flow of heat. So that's basically what we're going to be looking at. Spontaneity and entropy. What makes all things happen? Well, first of all, low energy. Low energy. Systems in nature tend to move toward lower energy, which we call enthalpy. So another word for low energy is enthalpy, and it has the symbol delta H. And when we talk about low energy, we talk about exothermic reactions. And entropy. Entropy, you know, is disorder. So things in nature tend to move toward more disorder. So high entropy. And when we talk about entropy in this unit, we're talking about delta S, change in disorder. If something is spontaneous, then it's something that happens on its own. And entropy is a measure of the amount of disorder. So in this next diagram, why does entropy happen? Well, entropy happens basically because of positional probability. Entropy happens because if in this situation, if we're talking about a gas and the cock stop is closed here, if I open it, what's going to happen? Statistically, the most probable arrangement is one in which the particles are most spread out. When we talk about entropy, let's review for a second solids, liquids, and gases. You know, in a solid, everything is structured, very organized, and in a gas, everything is spread out and much more further apart. And then in a liquid, things are a little bit closer together and they can move past one another. So here, gases have the most entropy, solids have the least entropy. So S is less than L, which is S less than G. In this next screen, using the gas that was in the previous diagram, they're showing you different microstate arrangements. So if all of those molecules represented 4 different types of gases, we could start with all of them on the left, and then when the cockstock is opened, maybe only A will go to the right, or maybe C will go to the right, B or D, and then as you go down here, you can see if 2 particles. So you have you have a lot of different types of combinations that can take place. So what you have to remember is that entropy happens due to positional probability. First law of the conservation of energy. Remember that heat flows from high to low, never the reverse. And we know from the first law of conservation of energy that we can't create or destroy energy. It simply changes from one form to another. And the second law, systems have an overall tendency to increase the entropy, so more disorder. A good example of this might be my desk, starting at the beginning of the day as opposed to the end of the day, or perhaps your bedrooms. In thinking about science, let's think about a sugar cube. When you put a sugar cube in hot tea, it dissolves. Why? Well, it spreads out. More disorder. One way to look at these two laws: the first law, you can't win, you can only break even. And in the second law, you can't break even. Simply that, because you're going to move toward disorder. And if you don't want disorder, you're going to have to put energy into the system to maintain the order. What is free energy? Well, free energy is the amount of energy available to do work. Sometimes this is called Gibbs free energy, because that's the guy that discovered it. So this is the amount of energy available to do work. This is a very important equation. Delta G equals delta H minus T delta S. So you've got Gibbs free energy is equal to the change in enthalpy minus the temperature, and remember, temperature must be in Kelvin, times the change in entropy. So let's think about what's going to happen. If my delta H is positive, then what type of reaction is that? That would be endothermic. If my delta H is negative, then that would be exothermic. If my delta S is positive, that means I'm more disordered. My delta S is negative, then I have more order, or less disorder. If delta G is positive, then the reaction is not spontaneous, and if delta G is negative, then that means that the reaction is spontaneous. When delta G equals 0, we have a special case. If delta G is 0, then the system is at equilibrium. And if that's the case, then we're going to use a different equation. And that equation is delta G is equal to the negative RT ln of K. And our R in this case is going to be 8.3145 joules per Kelvin dot mole. Now, you're going to have to watch your units on these problems, and they do this on purpose. Your delta G is always given in kilojoules. So this is in kilojoules, and your R value is in joules. So you're going to have to change your kilojoules over to joules in order to use this equation. Let's look at this next example. What is the boiling point of a solution where the heat of vaporization is 23.5 kilojoules per mole and delta S is 34.5 joules per Kelvin dot mole? Right away you should notice that you don't have an agreement of units. So if we're using the equation delta G equals delta H minus T delta S, what we know right now is, first of all, you have to realize boiling of a solution means that you are at phase equilibrium. If it's boiling, then, or you're trying to determine the boiling point, you've got liquid and gas. Both states are present. Therefore, if we are at phase equilibrium, then delta G is equal to 0. We're going to be solving for the temperature. So in this case, I'm going to have 0 is equal to, we're going to take our delta H, which is 23.5 kilojoules, minus T, and then delta S. If we change delta S to kilojoules, we can move the decimal 3 places to the left, and we're going to get 0.0345 kilojoules per Kelvin dot mole. I just want to show you this is also kilojoules per mole, and this is Kelvin. Rearranging the formula to solve for T, you wind up with T equal to delta H divided by delta S. So you've got T equal to 23.5 divided by 0.0345, and you wind up with a temperature of 681.6 Kelvin, and then they usually want you to report this as Celsius. So if you subtract 273, you're going to get 408 degrees Celsius. So I don't know what kind of solution we have here, but that's an extremely high boiling point. Okay, a couple of things that we need to remember. If you have an element in its standard state, that the delta H is 0. What do we mean by standard state? Well, standard state is 1 atmosphere and 25 degrees Celsius, which is 298 Kelvin. Those are standard conditions in a thermodynamic system. So if I had something that said carbon solid, that is its standard state, therefore its delta H would be equal to 0. And on the AP exam, they don't tell you that. You have to know that. Some students think that they can't solve a problem because they're given other delta H or delta S values, but they don't have one for O2. Well, oxygen is a gas in its standard state, therefore it would be 0. All right, let's look at what happens. We're going to see how the different signs of delta H and delta S affect delta G and whether or not a system is going to be spontaneous. And we're always going to refer back to delta G equals delta H minus T delta S. Whenever you get stuck, you can always put values into this situation. So let's look at this first one. If I have a positive delta H, it means it's endo, and if I have a positive delta S, that means I'm increasing entropy. So I have to determine whether or not this is going to be spontaneous. Well, when you look at this value, if this is positive, right, and my entropy is positive, okay, what's going to determine what happens to delta G? I've got a positive minus temperature times some positive value? Well, it should be easy to see that if my temperature is really small, then this net of T delta S could be small enough in where delta G would be positive. However, if my T is extremely high, then this T delta S product is going to be large, which means that my delta G would be negative. So in this case, delta G could be either positive or negative. However, it will only be spontaneous at high temperatures because it's the high temperature that's going to produce the negative delta G, making it spontaneous. Okay, what about if I had an exothermic reaction and I had a negative delta S, which means a decrease in entropy? Well, what's going to happen to my system then? If you look at this, if my delta H is negative and my delta S is negative, right? Then I have a negative minus a negative, which is really like adding. So if I have a very large T, it's like adding a very large positive number, which means theoretically if the T delta S combination is larger than delta H, then I could come out with a positive delta G. However, if my temperature is very low, then the product of T delta S would be smaller. So when I add it to delta H, then my delta G could essentially still be negative. So in this situation, I'm also going to be either positive or negative. And I will only be spontaneous at a very low temperature, because if T is very small, when it's added, when this negative value is added to this negative value, I can still remain negative. So this is at a low temperature that it will be spontaneous. Okay, if I have an endothermic reaction and I have negative entropy, so if this is positive, delta H is positive, and this is negative, then no matter what I do, my delta G, regardless of temperature and entropy, then my delta G will be positive. Then my delta G will be non-spontaneous because I'll come out with a positive answer. So no matter what I do, I'm going to add T delta S product to delta H. So I'm going to wind up with a positive delta G. So this is going to be positive. If this is exothermic and this is an increase in entropy, then let's look at what happens. So now this is, my delta H is negative and my delta S is positive. So this is negative, and it's going to be plus a negative value. I'm sorry, this is going to be negative, and this is going to be positive. Therefore, I will wind up with a negative answer, and it will always be spontaneous. So the best way to understand this chart is to actually use the equation and think about different values in the equation to predict whether or not the specific criteria that you're given will wind up leading to a spontaneous or non-spontaneous reaction. Okay, let's talk about calculating thermodynamic quantities. There are 4 ways to calculate delta H. We've already used calorimetry in Unit 5. We've already used Hess's Law, version 1, by adding the different reactions. We've done Hess's Law 2, where you take the sum of the products and you subtract the sum of the reactants. And we've done bond energies, bonds broken, bonds formed. Remember when we do bond energies, since this is kind of a review, in this one it's always the sum of the reactants minus the sum of the products. This is the only one. All the others, products minus reactants, bond energies, it's always reactants minus products. Note this value is usually given in units of joules per Kelvin, and you typically have to convert to kilojoules per Kelvin because delta H is given as kilojoules per mole, as is delta G. So we can calculate delta G 4 different ways. The most common is the one that we just talked about, delta G equals delta H minus T delta S. We can also calculate delta G by doing sum of the products minus the sum of the reactants and using the appendix in the back of the book for the different values. And this next one, delta G equals negative NFE. This is in the electrochemistry unit, which we haven't done yet. That's the next unit. And I spoke to you briefly about delta G equals negative RT ln of K, and that is when either your delta G, if you're trying to find delta G and you're given equilibrium information. So you can set up a K expression and solve it that way. So it says calculate delta H, delta S, and delta G for the following reaction. Use the appropriate appendices in your book to find individual values. So we're going to actually call this example 1, example 2, and example 3. And the first thing that we should do is take the back of the book and get the information that we need. So we need delta H information and we need entropy information. We need that information for SO2 gas, and we need it for O2 gas, and we need it for SO3 gas. So at the back of the book, delta H for SO2 is negative 297, and these are all, this is kilojoules per mole, and spontaneity is joules per Kelvin dot mole. For O2 it's 0 because it's in its standard state, and for SO3 it's negative 396. Then if we look up the spontaneity table, SO2 is 248, O2 is 205, and SO3 is 257. Okay, so in 1, we are going to calculate delta H. We can calculate delta H by doing the sum of the products minus the sum of the reactants. So let's start with our equation. On the product side, we have SO3, which has a delta H of negative 396, and there's 2 of them. So we've got 2 times negative 396. And that's going to be minus my products. O2 gas is in its standard state, so that's a 0. And we have SO2 with a value of negative 297, and there's 2 of them. So minus 2 times negative 297. And if we do the simple math on this, we're going to get negative 198 kilojoules per mole. For number 2, they want us to solve delta S. Delta S is also going to be sum of products minus the sum of the reactants. And in this case, we've got SO3. We have 2 of them with a value of 257. So 2 times 257. And that's going to be minus the sum of the reactants, in which we do have an oxygen at 205, and we have 2 SO2s at 248. So we've got 2 times 248 plus 205. So when we do this math, we get the product of this is 514 minus 701, which is going to give us negative 187 joules per Kelvin dot mole. Now, in the third one here, where we're solving for delta G, we have to have agreement of units, because delta G equals delta H minus T delta S. We have kilojoules per mole and joules per mole per Kelvin. So if I change this to kilojoules, it's going to be negative 0.187 kilojoules per Kelvin dot mole. Now I'm ready to plug this in, and I've got negative 198 kilojoules per mole minus T. We can assume it was standard temperature, so 298 times negative 0.187 kilojoules per mole dot Kelvin. So all my units cancel, and I'm left with delta G equal to negative 253.7. So this is indeed a spontaneous reaction. Okay, we're almost done. Let's take a look at free energy, pressure, and equilibrium constant. We can use delta G equals negative RT ln of K when we have an equilibrium constant. So consider the ammonia synthesis reaction, where delta G equals negative 33.3 kilojoules per mole of N2 consumed at 25 degrees Celsius. Calculate the value for the equilibrium constant. So this is basically a simple plug and chug. Let's write our formula. We've got delta G equal to negative RT ln of K. And for our delta G, we have negative 33.3, and this is kilojoules per mole, equal to negative R, which is 8.3145, and that's joules per Kelvin dot mole, times the temperature of 298 Kelvin, and we are solving for the ln of K. So if you take the product of the R value and the temperature, and then divide through, you're going to wind up getting here 13.44 equals the ln of K. Therefore, K is equal to 686,900, which is a really large K. Remember that there are no units for K. And the last problem. Calculate the value of delta G for the following reaction at 389 Kelvin, where the concentration of the ammonia, hydrogen, and nitrogen gas are as follows. So right away, you have to deduce, being that you're given concentrations, you can calculate Kc. This is from a previous unit. Kc is products over reactants. So you have the concentration of N2 divided by the concentration of NH3 times the concentration of, this is NH3 squared, sorry, and H2 cubed. So we can just plug in our concentrations. N2 is 3.01 divided by NH3, which is 2 squared, times the concentration of H2, which is 1.25, and we have to cube that. So we get a K value equal to 0.680. Now using delta G equals negative RT ln of K, we can solve for delta G, because this is our constant, times our temperature of 389 Kelvin, and we need the ln of 0.680. Solving for delta G, we get 1247 kilojoules per mole. So I'm sure that you will find that this math is a lot easier than what we just finished in the last couple of units. So this is back to straightforward plug and chug stuff. And that's the whole lesson for all of Chapter 16. Okay, see you next class.